So welcome everybody to our Gamma seminar. Today we have the pleasure to guest Adam Maskalaniec, who's going to talk about K-contact geometry and relativistic hydrodynamics. So Adam, thank you for accepting our invitation. Please go ahead, the floor is yours.
Okay, thank you for the introduction. Today I'm going to present my joint work together with Mihailo Hontarenko and Javier De Lucas on applications of K-contact geometry in relativistic hydrodynamics. So the outlook of my talk is as follows. At first, I will tell you a bit about the physical problem that motivates our research. Later, it will turn out that this physical problem is quite similar to what was already developed, but only for thermodynamics, namely the contact formalism for thermodynamics. Then it will justify the introduction of K-contact geometry to extend this thermodynamics to field theories, namely this K-contact relativistic hydrodynamics. And it turns out that the classical approach to contact geometry using only K-contact forms is not sufficient for our purposes, and thus we will need to use the novel distributional approach to K-contact geometry described by Javier De Lucas, Xavier Rivas, and Tomasz Sobczak. And later, using this formalism, I will proceed with the reduction theorem for certain symmetries that are satisfied by our physical systems. Okay, so the physical problem is the following one. We consider at first a flat Minkowski spacetime, R1 free, and we would like to construct a simple field theoretical model of relativistic hydrodynamics. So therefore, we would like to introduce some currents. The first one is the entropy current, also the next one, the baryon current, that measures the number and the flow of our particles. The next tensor, beta lambda, is the fluid for velocity divided by the temperature. It is convenient to use such a convention that we don't use this fluid velocity explicitly, because then our equations will look more similar to the K-contact ones we would like to analyze. So I'm already using this formulation in order to be closer to this K-contact formalism. This psi is the chemical potential of our particles, again divided by temperature. This double index T is the energy momentum tensor. And moreover, we introduce this pressure tensor. And the classical set of equations that describes this relativistic hydrodynamics is written here on that slide. So we have, in fact, a first equation that somewhat resembles the Gibbs equality from thermodynamics. The second equation, in fact, comes as a generalization of the first law of thermodynamics. And the last three ones are, in fact, classical conditions for vanishing divergence of our currents. And all the time I use the Einstein summation convention unless I state otherwise. So a very important feature of such a system is that it admits so-called pseudo-gauge transformations. Namely, it is possible to modify the tensors from the equations above in some ways so that they again satisfy those equations. So, for example, here we have a certain case of a pseudo-gauge transformation. Namely, we can add to this energy momentum tensor that satisfies our equation from the page number 1, something that resembles a full derivative, namely this derivative of this sum of antisymmetric tensors. And then one may easily verify that this divergence of the energy momentum tensor is again 0. So this is quite unusual in thermodynamics, because in thermodynamics it turns out that these quantities are determined uniquely. So as I mentioned before, in thermodynamics we can see quite similar equations, in fact. So the first law of thermodynamics can be expressed in this form highlighted as the equation number 2. And in fact, mathematically, it's a condition of vanishing of certain differential form. The differential form that it turns out to be, in fact, a contact differential form. Then, since this law of thermodynamics is valid for equilibrium states, if we consider such equilibrium states, we would like to describe processes that are integral, that are described by curves, such that the tangent vectors of that curves vanish when we apply this differential form eta. Okay, so therefore we would like to restrict our system to a submanifold of our contact manifold with this property that eta vanishes on that submanifold. Okay, in contact geometry, obviously eta defines a maximally non-integrable distribution, and thus we need to find and choose a suitable submanifold, integral submanifold of eta of a smaller dimension. And in contact geometry, every Lagrangian submanifold, it is a classical result that can be found, for example, in the book of Arnold on classical mechanics. Every such Lagrangian submanifold, namely an integral submanifold of eta of maximal dimension, can be locally expressed using a so-called generating function. And physically, this generating function of Lagrangian submanifold that gives us a parametrization of such a submanifold in this coordinate way is just our equation of state. Okay, so the picture is the following. We have a set of equilibrium states in our thermodynamic space. This thermodynamic space is a contact manifold, and this set of equilibrium states is just a Legendrian submanifold of this contact manifold. And our equilibrium thermodynamic process is just a curve, a smooth curve that is contained in such submanifold. Then we can describe these curves as integral curves of Hamiltonian equations of our contact forms. So this is this contact approach to thermodynamics, summarized really briefly. Okay, so since, as we already observed, our equations of relativistic hydrodynamics are already quite similar to what we see in contact geometry, especially this equation that I underlined now looks a little bit like a definition of a K-contact form for a certain manifold. It resembles this canonical form written in Darboux coordinates. So therefore, we had an idea to create a similar formalism for relativistic thermodynamics, as it was already done for thermodynamics using contact geometry, but we had to apply this K-contact geometry. And this short introduction motivates the following definition. I will recall a kind of theoretical minimum on K-contact geometry that is necessary to understand what happens later. So, a K-contact form on a manifold M is an RK differential form such that kernel of this RK-valued differential form is a regular non-zero distribution of corank K. Kernel of the exterior derivative of eta is a regular distribution of rank K, and the intersection of those both kernels is zero. So in other words, Tm is just kernel of eta plus kernel of the eta. Okay. So from now on, I will write this RK-valued differential form using this tensor product convention and this Einstein summation over upper and lower indices. So an important property of every K-contact manifold is that it admits a unique family of vector fields R alpha, called the Reb vector fields, such that they are dual to these K-contact forms, and they vanish whenever we contract them with the exterior derivative of the K-contact form. And moreover, those vector fields commute with each other. K-contact manifolds are very general, and they might have really, I would say, unusual dimensions. So while, for example, symplectic manifolds are always even dimensional and contact manifolds are always of dimension 2n plus 1, the K-contact manifolds may have very different dimensions, and there is one condition, namely existence of this polarization, that restricts our very big class of K-contact manifolds to a smaller set. So moreover, I say that a K-contact manifold of dimension n plus kn plus k admits a polarization if the K-contact distribution kernel of eta admits an integral distribution V of rank n times k. And this condition is very convenient when we want to prove any theorem on K-contact manifolds, because then, assuming our K-contact manifold admits a polarization, it turns out that we have a Darboux theorem for K-contact manifolds that allows us to present our K-contact form in a very convenient, very standard way. And this really simplifies all further calculations. Okay. So now I'm going towards formulation of an analog of Hamiltonian equations for K-contact geometry. And to do it, I would like to introduce some notation. So in my presentation, this pi will denote canonical projection from the kth direct summand of the tangent bundle of M to M. And moreover, this pi with this lower index alpha will denote the projection from this direct sum onto its alpha direct summand. And using that, I'm going to define K vector fields and formulate the so-called K-contact Hamilton-de Donderweil equations for K-contact geometry that will serve me as an analog of Hamiltonian equations for contact or symplectic geometry. So a K-vector field is just a section of the fiber bundle, the K times the direct sum of the M over M. So in fact, this K vector field is just a collection of K ordinary vector fields. And I write X alpha for the composition of pi alpha with X. So it's the alpha component of our K vector field. So now, whenever we have a K vector field and an RK valued differential form, we may define a contraction of this K vector field with the RK valued differential form using this Einstein summation convention. Okay. So our K-contact Hamilton-de Donderweil equations will be formulated for K vector fields, but we would like to describe some field theoretical problems. And thus, we would like to formulate our equations for fields. So in our case, the K-contact manifold plays the role of a configurational space of our system. And the domain of our fields is the space-time. We consider just the flat case, so our space-time is just RK. And every such field admits a so-called first prolongation, namely a K-vector field that is defined in a way that we apply this tangent map of psi to the distinguished coordinate vectors on RK. And then we say that an integral section of a K-vector field is a map psi such that, in fact, this X composed with psi is the integral, is the first prolongation of our field psi. Okay. And using those and using this notion of a K-vector field, we may define a K-contact Hamiltonian system. The K-contact Hamiltonian system is given by a K-contact manifold described by a K-contact form and a smooth function on M that is our Hamiltonian. The K-contact Hamiltonian Hamilton-de Donderweil equations are written here, and they are an extension of contact Hamiltonian equations. So in particular, for K equal 1, we simply obtain the contact Hamiltonian equations. And what is really an interesting feature of such K-contact Hamilton-de Donderweil equations is that they admit solutions, although these solutions might be non-unique, especially when K is greater than 1. Then it turns out that those equations are non-unique, and the number of degrees of freedom of those solutions is k minus 1 times kn plus n. Okay, so this is another feature of this k-contact Hamilton-de Donderweil equations that suggests that they might be a proper framework for our physical problem, because we expected that the pseudo-gauge transformations are allowed because those solutions of Hamilton-de Donderweil equations are non-unique. So this characteristic feature of the Hamilton-de Donderweil equations also really well corresponds with our physical problem. And it was another reason we decided to apply this k-contact geometry to relativistic hydrodynamics. And I will briefly recall a proof of this fact. Although it's a standard result, the proof introduces us two maps that will be necessary later. So since our manifold M is indeed a k-contact manifold, then every k-vector field X can be uniquely decomposed into its k-contact part xc that takes values in this k-contact distribution, and this part xr that takes values in this distribution kernel of d eta that is called the rep distribution. And then we may observe that one can write k-contact Hamilton-de Donderweil equations in this simplified form. So what is the difference between the previous formulation is that I acknowledge that whenever we contract something from the red distribution with kernel of the eta, then we get 0. And similarly for eta, I can omit this part xc. Okay, so hence I can interpret these k-contact Hamilton-de Donderweil equations in terms of these two vector bundle maps. So the first one, row 1, maps the k times kernel of eta into the annihilator of the rep distribution, and the map row 2 takes the k times the direct summand of the rep distribution into m times r. So the second map is clearly surjective, and this existence of solutions of the k-contact Hamilton-de Donderweil equations for any Hamiltonian H is essentially equivalent to the surjectivity of the first map, row 1. Okay? So what remains to prove is that this row 1 is surjective. And in fact, using this definition of the k-contact manifold, one can prove that row 2 is surjective. Because if row 1 was not surjective, then this co-distribution span by d eta alpha of w, with w being in kernel of eta, would be strictly contained in this annihilator, at least at a single point. And then we would have a vector in the kernel of eta such that d eta evaluated on this vector would be 0. Yes, d eta evaluated on that vector and restricted to the kernel of eta. Since when we evaluate d eta on the rep vector fields that already span the rep distribution, we get 0, then it follows that this v is both in kernel of d eta and kernel of eta, and then it is a contradiction with the definition of the k-contact form. Okay, so therefore we proved that our map row 1 is surjective, So what remains to be calculated is the dimension of the kernel of row 1 and the kernel of row 2 that gives us this number of degrees of freedom. Because this modification by some elements from the kernel essentially amounts to another solution of our Hamilton, the Donderweil equations. So just one remark that these solutions are unique only in the contact case for k equal 1. So as I previously mentioned, Legendrian submanifolds for ordinary contact manifolds play the role of physical sets of equilibrium states for our thermodynamic systems. So if we would like to extend this notion of equilibrium states for our relativistic hydrodynamic case, then we need to construct a corresponding notion of Legendrian submanifold in the case of k-contact geometry. And now it's time to give a precise definition. So, given a vector subspace Ex in the k-contact distribution at the point x, we say that this Ex has an orthogonal complement relative to eta that is a vector space of vectors from the k-contact distribution such that d eta evaluated on this vector from the orthogonal complement and any other vector wx from E is equal to 0. So in fact, this k-contact orthogonal is nothing more than a k-symplectic orthogonal on a k-symplectic space kernel of eta, whose k-symplectic form is simply d eta. So then we mimic the classic definitions, and we say that E is isotropic if it's contained in its orthogonal complement, and moreover we say that E is Legendrian if E is isotropic and it admits an orthogonal complement F such that F is also isotropic. This condition here is equivalent to saying that F is also isotropic. So Legendrian space is an isotropic space with an isotropic complement in the kernel of eta. So then we extend these notions to distributions and consequently to submanifolds. And we say that a submanifold is Legendrian if all its tangent spaces are just Legendrian vector spaces. So the first observation is that in the k-contact setting, unlike in the contact setting, whenever we have even a polarized coorientable contact manifold, so a polarized case for k-contact manifold is already very specific, but still, even then, we may find some Legendrian submanifolds of different dimensions from n up to n times k. So this is different because for the contact case, these Legendrian submanifolds are always of dimension n. However, quite fortunately, whenever we have a Legendrian submanifold of a k-contact manifold, then it is maximal with respect to this inclusion relation. Okay. So now we mimic this contact geometrical approach to thermodynamics, and we extend it to this K-contact relativistic hydrodynamics. So then, given the generalized Gibbs relation number 7 and this generalized first law of thermodynamics for the relativistic hydrodynamics, we use this second identity, this generalized first law of thermodynamics, to define our K-contact structure in the following way. What is really different from my original set of equations is that in order to fit those equations in the K-contact setting, I had to add one variable, v, that might be interpreted physically as a volume of the system. So I use now some extensive variables instead of intensive variables. And this is quite strange modification from the physical point of view, because our physical volume is in fact given by this Lorentzian metric on our space-time and not by any other field. So this is a bit artificial, and later we would like to get rid of that additional variable. However, the good news is that such K-contact form admits polarization. So our K-contact manifold is a polarized K-contact manifold. Okay. So then one may calculate that when we consider first prolongations of fields from whose domain is the spacetime R1 free to the configurational space that is our K-contact manifold, then those Hamilton-de Donderweil equations applied to our first prolongation of that field recovers these other equations from our relativistic hydrodynamics. So this example perfectly fits into the K-contact geometrical framework. So now those pseudo-gauge transformations are really interesting for us because some modifications, for example, of the energy momentum tensor, might have physically measurable results. So if we modify the energy momentum tensor, some physical properties of our fluid, such as viscosity, might change, and it is possible to measure it. So therefore, we would like to classify those degrees of freedom of our pseudo-gauge transformations. So now we would like to pose a question. So suppose we have a Hamiltonian H and a set of equilibrium states given by a Legendrian submanifold. So how many degrees of freedom are still available, assuming that we would like to fix a condition that our solutions must be tangent to that Legendrian submanifold, okay? So at first we observe that if an image of a solution to Hamilton-de Donderweil equations with a Hamiltonian H is tangent to L, then it is necessary that this Hamiltonian must vanish on that submanifold. And this is a simple observation, but an important theorem we managed to prove is that if L is a Legendrian submanifold and H is restricted to L, then these Hamilton-de Donderweil equations for K-vector fields really admit some solutions that are tangent to L. And moreover, if our K-contact manifold is a polarized K-contact manifold, then we are able to calculate the number of these pseudo-gauge degrees of freedom. So it turns out that the Hamilton-Dondel equations for Hamiltonian that vanishes on our Legendrian submanifold are unique if and only if this dimension of the Legendrian submanifold is equal to n. Okay, maybe I will skip this proof because I wouldn't like to extend our seminar for too long time. So now I will move to this example. Yeah, we managed to prove this theorem by an analysis of this bundle mappings of this bundle maps on the level of tangent spaces. So doing in fact a K-symplectic linear algebra, we managed to calculate the dimensions of the kernels of our mappings, assuming that our solutions need to be tangent to the Legendrian submanifolds. And as I said before, it is possible that Legendrian submanifolds may be of different dimensions, but it turns out that at least for a class of important physical examples, we managed to calculate that these physical examples correspond exactly with Legendrian submanifolds of dimension equal to n. So in fact, in contact thermodynamics, it is also a matter of choice that we would like our equilibrium states to be Legendrian submanifolds. It would be possible to choose a different class of manifolds that are necessarily isotropic submanifolds, but might be of different dimensions. Then, for example, solutions to some thermodynamic equations may not exist. Yeah, and here it seems that this most probable and the most convenient choice for physics are exactly these Legendrian submanifolds of dimension equal to n. So we considered a K-contact manifold with coordinates being this extensive entropy current, pressure current, volume, the chemical potential, particle current, velocity divided by temperature, and the extensive energy momentum tensor. Then this K-contact form can be expressed with this equation. And it turned out that the equations derived by physicists to describe this so-called Bjorken flow model exactly correspond to the Legendrian submanifolds of dimension n. So this example really shows that our K-contact framework is a good framework for the physical problems. However, as I told you before, we managed to apply our K-contact formalism, but paying a cost of introduction of those so-called extensive variables. So now we would like to add a so-called scaling symmetry. And this scaling symmetry, physically speaking, would allow us to pass again from these extensive variables to the intensive variables that really have a significant physical meaning for our relativistic hydrodynamics. Because as I told you before, this volume field is this introduction of the volume field is some kind of a mathematical trick that allows us to fit our equations in the k-contact formalism. So I say that a k-contact Hamiltonian system admits a scaling symmetry that is a free and a proper action of this multiplicative group of real numbers, such that this action scales our k-contact form by this positive real number, and it scales in a similar way our Hamiltonian. Then in coordinates, it turns out that we may calculate that our solution of these k-contact Hamilton-de Waal equations is a k-vector field that is projectable with respect to this scaling symmetry, and then it corresponds to our original set of equations. So our big picture is here. So I had a physical problem and I extended it a little bit. And then I was able to formulate it similarly in the language of k-contact geometry, as it can be done for thermodynamics using ordinary contact geometry. Then, applying those Hamilton-de Waal equations, one may solve our physical problems and moreover analyze the number of these pseudo-gauge degrees of freedom. And then using the scaling symmetry, we would like to project our solutions to obtain some physically relevant solutions. So now I would like to find another way. So I would like to reduce this k-contact Hamiltonian system with respect to our scaling symmetry, so that I obtain yet another k-contact Hamiltonian system, and then I can work directly with those intensive formulation of our physical problem. Okay. So in order to do that, I need to use this distributional approach to k-contact geometry, because let's say normal reduction theorems for k-contact geometry would not apply to my scaling symmetry, since this k-contact form, eta, is not preserved by this scaling symmetry, but our k-contact distribution, the kernel of eta, obviously is invariant with respect to this scaling symmetry. Okay, so a k-contact distribution is a distribution in a tangent bundle Tm, such that for every point x there is an open neighborhood, that this distribution locally is given by k-contact forms. However, globally, it's not necessarily true. Okay. So then it was proved in paper by Javier de Lucas, Xavier Rivas, and Tomasz Sobczak that there are some conditions that can be expressed purely in the language of distributions that allow us to guarantee that a certain distribution is indeed a k-contact distribution. So the first condition is the so-called maximal non-integrability, namely, given a distribution D, it is maximally non-integrable whenever this morphism rho from V times D to Tm divided by D is non-degenerate, namely, for every point and every vector from dx, we can find a vector w in dx such that this rho of vx and wx is not equal to 0. So this condition can be understood as follows, that given any vector in D, we can find another vector in D such that their commutator is no longer contained in this distribution D. Okay. So if D is a distribution of a corank 1, then D is maximally non-integrable if and only if D is a contact distribution. So if we would like to characterize the contact distributions for k equal to 1, then this first condition of maximal non-integrability is equivalent to D being a contact distribution. However, in the k-contact case, we need yet another condition. So we need to analyze Lie symmetries of the distribution. So a Lie symmetry of a distribution is simply a vector field that preserves this distribution under the Lie bracket. So every k-contact distribution on M admits an open neighborhood U of every point X, such that we have k vector fields S1 as k that are Lie symmetries of this k-contact distribution, and moreover, those vector fields commute with each other, and D summed with the vector with the distribution spanned by these vector fields is equal to Tu. Okay, we have this direct summand, and these vector fields in that case are in fact these vector fields. Okay, and it turns out that every distribution D on M is a k-contact distribution if and only if it is maximally non-integrable, and around every point X there is an open neighborhood U, such that we have this system of k non-vanishing Lie symmetries that commute with each other. So this gives a very clear strategy for the proof of this reduction theorem for scaling symmetries. So if we are given a scaling symmetry on a co-orientable k-contact manifold, namely a k-contact manifold that admits a global k-contact form and the free and the proper action, that is our scaling symmetry, then we would like to construct a k-contact structure on the quotient by this action. But this k-contact structure will not be necessarily co-orientable, but will be k-contact in this distributional sense. Okay. So to prove such a reduction theorem, I need to introduce the momentum maps for these scaling symmetries. This momentum map is simply a map from our k-contact manifold to Rk, defined as a contraction of our k-contact form with the fundamental vector field of our scaling symmetry. Okay. So now to set this reduction theorem, I need some assumptions. So at first, I assume that I have a polarized co-oriented k-contact manifold of dimension k plus n k plus n, and a scaling symmetry such that 0 is a regular point of our momentum map of the scaling symmetry. And moreover, the restriction of the fundamental vector field of this scaling symmetry to this level set of our momentum map is not contained in the restriction of the polarization. So our scaling symmetry needs to be, in a sense, transversal to our polarization. Then it turns out that we have a natural candidate for a reduced k-contact distribution on a manifold that is this level set of the momentum map, quotient by our scaling symmetry. Okay, this natural candidate is the intersection of the kernel of eta, our k-contact distribution, with the tangent space to this level set of our momentum map, then quotient by the distribution spanned by our infinitesimal generator of this scaling symmetry. Okay. And moreover, if this scaling symmetry leaves our polarization invariant, then this polarization descends to a polarization of our reduced manifold. And this is our reduction theorem. So how do I prove this theorem? So at first, I need to verify that our action restricts to this level set. And I do it calculating the Lie derivative of our momentum map. And it turns out that for the scaling symmetry, the Lie derivative of the momentum map is again the momentum map. So psi is tangent to the level set of the momentum map only if this level set corresponds to the value 0, okay? So later, if we would like to have a k-contact distribution, this distribution has to have certain dimension, namely the dimension of our reduced manifold minus k. And in order to ensure that this dimension is correct, I need to verify that the k-contact distribution, the original k-contact distribution D, summed with the tangent space to this level set of our momentum map, is the whole tangent space, the M, because then we would be able to write here k plus nk plus n and use this dimension formula for the intersection of vector spaces to obtain a correct dimension. Okay, so I proceed by contradiction and I assume that I have a vector z that is not contained in this sum. And then obviously we have an one form theta that doesn't vanish in a neighborhood of x and annihilates both this tangent space to the level set and our k-contact distribution. Thus, theta is simultaneously expressed by etas and by dj alphas with some smooth coefficients, with some coefficients that are smooth functions. Okay, and then using the property of the scaling symmetry, I calculate that the Lie derivative of eta can be expressed using this momentum map. So I can replace my dj alpha with eta. Okay, so then it turns out that we obtain this identity that has to be satisfied on the whole neighborhood. Then, without loss of generality, we can replace this difference of f alpha and g alpha with a smooth function h alpha. Okay. And then, when we contract both sides with the left vector fields, we get that h alphas are necessarily equal to 0. And thus, g alpha times the contraction of v eta alpha with psi is necessarily equal to 0. And using calculations in their book coordinates, then we may verify that all g alphas are also equal to 0. Okay. Then we need to verify that psi is a Lie symmetry of the j, but it is true since psi is tangent to this level set. It preserves this distribution, and moreover, since the scaling symmetry preserves the k-contact distribution, it also preserves D, so it also preserves the intersection. So we have a proper candidate for a reduced k-contact distribution. That is this distribution d prime, that is the intersection of the k-contact distribution with the tangent space to the level set. I'm sorry for a typo, but here we should have not t, but j. And then we have a distribution that has a proper dimension. So it is a good candidate to be a k-contact distribution. Okay. And then, in fact, by very similar means as previously, as at the beginning of the proof here, I verify the conditions that ensure us that our distribution is indeed a k-contact distribution. Okay, so I proceed these calculations on differential forms using the property of our scaling symmetry. What is also a quite tricky part of the proof is that I need to construct some new infinitesimal, some new symmetries of our distribution, because the rep vector fields are not projectable with respect to that action. And therefore, I must modify those rep vector fields to obtain new candidates for these rep vector fields. But these are, again, similar calculations. If you want, I have a full version of that proof, so we can discuss some technical issues later, okay? So what is an important conclusion is that using this distributional characterization of the k-contact distributions, we may reduce k-contact manifold defined by a global k-contact form to another k-contact manifold that may not admit a global k-contact form. However, at least locally, if we are able to find a one homogeneous function that is non-vanishing, say a function f, then when we divide our original k-contact form by this one homogeneous function, we obtain something that is zero homogeneous and thus invariant with respect to our scaling symmetry. And therefore, at least locally, we may recover the form of our k-contact structure in this classical language, okay? So it turns out that when we would like to reduce our extensive k-contact thermodynamics with respect to our scaling symmetry, then, well, this scaling symmetry is intended to scale only the new extensive variables, namely the entropy, volume, number of particles, and the energy momentum tensor. Yes. So here I have this scaling symmetry that scales exactly those extensive variables. Yeah. Okay. And then, indeed, it turns out that if we at first restrict our submanifold to the level set of the momentum map, then we obtain a manifold with new coordinates with tildes, and moreover, this momentum map can be expressed using this so-called Gibbs-Duhem identity that was written on the first slide here. So this momentum map really naturally appears in physics and has a very clear interpretation of this famous Gibbs-Duhem identity. Okay. And moreover, it turns out that this k-contact form that is defined now only locally, whenever we can find a non-vanishing non-vanishing one homogeneous function, is the k-contact form, eta prime here, that corresponds to an equation written in the beginning here. So this reduction procedure allowed us to find a distribution that, at least locally, is described by these equations known from the work of physicists. So, what is still left to be done and what is still interesting in the topic? So, at first, I would like to extend my theory by formulation of k-contact Hamilton-de Donderweil equations in terms of jets of sections of a fiber bundle whose total space E is a k-contact manifold. So then, from this physical point of view, we replace our K here with a manifold that might have non-trivial topology or a non-trivial metric structure, and that might be interesting from the point of view of analysis of our examples in curved spacetime. So this is very important, not only from a mathematical point of view when we would like our equations to be coordinate-free and intrinsic, but it's also important from the point of view of physical applications. Moreover, I would like to analyze the behavior of pseudo-gauge degrees of freedom under this reduction procedure. And the next part of my idea to develop this theory is to introduce the k-contact extension of Sasakian geometry, because Sasakian geometry also plays a very important role in contact thermodynamics, since it allows us to describe these equilibrium points and also dissipation in our physical systems. Okay, so thank you for your attention. It's now time for the questions.
Thanks, Adam, for your presentation. So, as you said, are there any questions or comments?
Well, a little bit off topic question.
Please go ahead.
Or over future research question. I know your other research topic, Adam, is graded differential geometry or supergeometry, however you want to call it. So have you thought at some point combining your both research topics and, I don't know, studying hydrodynamics of fluids with particles with spin or something like that?
Well, it is possible to be done here, but at first I would like maybe to connect those topics in the following, I would say, quite more natural way. So not as an extension, but as an application of this graded geometry theory to what I already have. Because you may recall that if you consider any graded manifolds or supermanifolds, then we have a formulation of that theory in the language of monoid actions of these real numbers on our manifold. Yeah.
Of course.
So in fact, those scaling symmetries are already some kind of grading on our manifolds. Yeah. So at first, I would like to investigate my reduction procedure from this graded point of view. So this is the first one. But also, as you mentioned, this extension of this k-contact manifolds to the graded case also has a lot of sense, since this relativistic hydrodynamic equations, as I know, from my friend, my collaborator, Mikhailo Hontarenko, who is a real physicist, that calculates those equations for applications, for example, in heavy ion collisions. Then he told me that, well, these relativistic hydrodynamics equations can be applied to calculate some quantities in collisions of particles in accelerators, yeah? So then obviously they also analyze particles with spin, and this is the point, this is the place where supergeometry can come into play, yeah?
Thank you.
Okay, thank you for the question.
Are there any more questions or comments? No? Okay, so thank you again, Adam, for your talk, and thank you all for attending. We will see you next week with our speaker, Galina Filipuk. So thank you again, and see you next week. Bye.